Here, we are going to solve for the value of A in this linear system that will tell us two different sets of solution. So we are going to look for the value of A that could make this linear system with exactly one solution. We're going to solve for A that will make the solutions for this linear system with infinitely many solution, and a situation where there can be no solution for this linear system. In order for us to do this, let us try to come up with the augmented matrix for this. But please don't forget that the A representation is for the constant. So we're going to place the variable A as a constant as our entry of our augmented matrix. So we have it here. We have 1, 2, -3, and 4 for the first equation. Next, 3, I have -1, 5, and 2. And for the for the third row, we have 4, 1, and A squared, that's squared, minus 14 as a representation for the coefficient of this, and then A plus 2. So we are going to look for the value of A that can make create a infinitely many solutions, exactly one solution, or no solution. So the goal here is to come up with a row echelon form. That's the thing we need to do, because you would like to come up with the third row where we could look at the direct relationship of the remaining leading coefficient here that will be represented by A and its equivalent result for the fourth column. So again, let's apply the Gaussian elimination to come up with row echelon form. We're going to make this 0 and 0, and since for the first row we already have leading 1, so we don't need to divide the first row with anything, but we could apply this. Let's multiply -3 to row 1, add it to row 2 for a new row 2, and let's multiply -4 for row 1 plus row 3 to have a new row 3. In this case, we are going to come up with results that will make this first entry and for both second and third row to be equal to 0. So it will be like this here. So the first row is still 1, 2, -3, and 4. But for the second row, -3 times 1 is -3 plus 3, 0. Then apply to the next. -3 times 2 is -6 plus -1 is -7. The -3 times -3 is 9 plus 5, I have 14. -3 times 4 is -12 plus 2 is -10. That's for the second row, applying the set of declared operation. Next, let us try to continue with the next. -4 times 1 is -4 plus 4, 0. Then, let's have -4 times 2 is -8 plus 1, I have -7. Then -4 times -3 is plus positive 12. Plus this, so we'll just be adding here -14 plus 12. So I have here A squared minus 2. Okay? And finally, -4 times 4 is -16 plus this here. So I have A minus 14. Next is to make this as equal to 1. So we'll multiply -1/7 to our row 2 for us to have a new row 2. And let me integrate another operation here, but applying not to this new row 2, but for the original row 2 here. Let us have -1 times row 2 plus, that's plus row 3 to have a new row 3. Okay, again, this row 2 here is the original row 2, not this one. But of course, you could separate those two if you would like to. But let me continue it here. So the first row is still 1, 2, -3, and 4. The second row will be multiplied to -1/7. This is 0. This is positive 1. -2. and I have here positive 10 10 sevenths, right? Okay, so 10 sevenths here. So next you will have for the third row, negative 1 times, of course, 0, 0, so it's 0 here. Negative 1 times negative 7 is 7 plus 7, 0. Negative 1 times 14 is negative 14, and then you have minus 2, so you have a squared minus 16. Negative 1 times 10 is positive 10, and you will add it to negative 14, so you have a minus 4. That's 4, sorry. 4. So let's look at the relationship of these two entries here. Let me write it here. A squared minus 16 and a minus 4. Okay? So if this is 0 and this is 0, meaning I will have a version of 1, 2, negative 3, 4, 0, 1, negative 2, 10 over 7, 0, 0, 0, 0. Okay? If these two are zeros, just like in the previous examples last time, we have three variables here. For the number of rows is less than the number of variables. We have x, y, and z. This means that if these two are zeros, we expect to have infinitely many solutions. Okay? We have infinitely many solutions. So when can these two be equal to 0? So let's try to compute this one here. So for infinitely many solutions, a squared minus 16 must be 0, and a minus 4 must be equal to 0. So a can be 4, and this here, I have two results here. A plus 4 equal to 0, a minus 4 is equal to 0. You have two possible values for a, negative 4 and positive 4. Look at the two situations. Of course, we could have negative 4 here. But if we are going to apply negative 4 here, this will not become 0. That is negative 8, right? So this is the only value that will make it true, that when applied to a squared minus 16 and a minus 4, that's a is equal to 4, we'll have infinitely many solutions. So for the entire linear system to have infinitely many solutions, a must be equal to 4. Now there is also another value here. A is equal to negative 4. If we have negative 4, okay, we have negative 4 squared minus 16. That would be equal to 0 because 16 minus 16 is equal to 0. This entry here will become 0. But for a minus 4, negative 4 minus 4 is negative 8. This is negative 8. Notice that we have a situation like this last time. If we have a matrix, 1, 2, negative 3, 4, 0, 1, negative 2, 10 sevenths, 0, 0, 0, and negative 8. All entries here are 0, but we have a resulting value of non-zero. This means this should have no solution. So when can we have no solution? That is if a is negative 4. That is the value we substituted here. So we already have two situations. We have infinitely many solutions if a is 4. We have no solution if a is equal to negative 4. And we are left with other values. So there can be exactly one solution for any value of a which is not equal to 4 and a is not equal to negative 4. So these are the results for this given situation. Solving for this linear system, predicting the value of a that could make, number 1, infinitely many solutions, number 2, no solution, and number 3, exactly one solution. Okay? Thank you for watching.